How does a lifeless ball of fire become a living world capable of memory? Oceans. And thought 4.5 billion years ago, Earth began as chaos molten rock. Violent impacts and endless time. A single collision gave rise to the moon. Water arrived from deep space. The atmosphere slowly changed, allowing the first fragile forms of life to take hold, from simple cells to vast forests, from mass extinctions to new beginnings. Chance and catastrophe quietly shaped everything beneath our feet. Tonight, we'll follow that long, unlikely journey, not as a race through history, but as a calm reflection on how time, physics, and survival work together to build the only home we've ever known. If this kind of deep time science speaks to you, please like and subscribe. Now, let's begin. The universe is vast, quiet, and seemingly indifferent across unimaginable distances. It stretches cold and empty, dotted with stars but offering little sign of life. As far as we know, there is only one place where matter learned to breathe, to grow, to remember itself. One small planet, circling an ordinary star. The question of why this happened here and not elsewhere does not have a simple answer. It is written slowly, patiently, across billions of years. Deep within the planet's own past, to read that story, we have to step away from the present, away from familiar coastlines and skies. We have to travel back to a time before continents had names, before oceans knew how to rest, before the idea of life even existed. We move through ages where continents drift like living things, carried by heat rising from deep below. We pass through eras shaped by impact and extinction, by fire and ice, by forces that seem cruel but prove essential only by watching Earth assemble itself. Moment by moment, can we begin to understand why this planet became a home? Nearly 5 billion years ago, the scene is stark and unfinished. There is no Earth yet, only a newborn star, our sun, burning at the center of a rotating disk of dust, gas, and shattered rock. This disk is the leftover material from the star's formation. Restless and unstable, gravity is already at work. Though nothing looks organized, dust grains collide gently at first, sticking together through static forces, forming tiny clumps. Over time, these clumps grow. Pebbles become rocks. Rocks collide and merge, sometimes breaking apart, sometimes surviving. This slow, chaotic process is known as accretion, and it is how planets begin. At first, it seems impossible that something as layered and dynamic as Earth could emerge from such disorder. But gravity does not hurry, and it does not forget. Over millions of years, countless collisions concentrate mass into larger bodies. Eventually, one of those growing bodies becomes dominant in its orbit. This is the early Earth, fully formed around 4.54 billion years ago. Yet nothing about it resembles the world we know. The heat generated by constant impacts, combined with radioactive decay deep inside the planet, keeps the surface molten. Temperatures soar beyond 1,200 degrees Celsius. There is no breathable atmosphere, only thick clouds of carbon dioxide. nitrogen, and water vapor released from the interior through volcanic outgassing. The planet is wrapped in toxic heat. Solid ground barely exists. The surface behaves more like a restless ocean of lava than land. And still, Earth's story is only beginning. Another planetary body approaches, born in the same crowded region of the young solar system, roughly the size of Mars. It moves at nearly 15 kilometers per second, drawn in by gravity as it nears. Its gravitational pull begins to distort Earth itself, stretching and deforming the molten surface. When the collision happens, it is not a clean impact, but a merging of worlds. Vast amounts of material from both bodies are vaporized or flung into space. For a time, Earth is surrounded by a glowing ring of debris. This debris does not disperse. Instead, gravity once again gathers it. Over roughly 1,000 years, fragments collide, melt, and merge. A new body forms in orbit. The Moon is born. This moon is far closer than the one we see today, only about 22,500 kilometers away. Its proximity has profound effects. Its gravitational pull stabilizes Earth's tilted axis, preventing wild swings that would make climate chaotic. At the same time, the energy of the impact has set Earth spinning at an extraordinary rate. A full rotation takes just 6 hours. Days pass quickly. Nights barely have time to settle, and the planet's shape bulges slightly at the equator due to centrifugal force. As Earth spins, it also begins to cool. Heat slowly escapes into space. Heavy materials sink inward, forming a dense core, while lighter materials rise, creating the first layers of crust. This internal separation, known as differentiation, is essential. It allows Earth to generate a magnetic field, which will later shield the surface from harmful solar radiation. Time stretches forward. Millions of years pass. Then comes another defining era. Around 3.9 billion years ago, Earth enters a period known as the Late Heavy Bombardment. Debris left over from the solar system's formation rains down relentlessly. Impacts scar the surface, but they also deliver something unexpected. Some meteorites contain tiny crystals that trap microscopic droplets of water. Others carry carbon-based molecules, including amino acids. Each individual delivery seems insignificant, but over more than 20 million years, the accumulation becomes substantial. As Earth cools further, surface temperatures fall to around 70 to 80 degrees Celsius, allowing liquid water to persist. Pools form, rain falls, water gathers in low places, filling basins that will become oceans. Every drop of water on Earth today carries this ancient history. The water is billions of years old, carried across millions of kilometers of space before settling here. It is older than any mountain, older than any living cell. The planet now appears calmer, but it remains restless. Rapid rotation drives fierce winds across the surface. The moon's closeness generates enormous tides, pulling oceans into motion, sweeping water across continents that are still forming. These tides churn minerals, mix chemicals, and distribute heat. Over time, the moon slowly drifts away. Tides weaken, and Earth's rotation slows. The planet settles into a more stable rhythm. By 700 million years after its birth, Earth's surface is largely covered by water. Beneath these oceans, volcanic activity continues. Molten rock rises through cracks in the crust. Erupting underwater, lava cools quickly, forming solid structures that pile upward. Volcanic islands emerge, then merge, forming the earliest continents. These land masses are small and unstable, but they introduce something new: shallow coastal environments where chemistry can grow more complex. Meteorites continue to fall. Around 3.8 billion years ago, their contribution becomes critical. Along with water and carbon, they deliver a diversity of organic molecules. These materials sink into the oceans, dissolving into the depths. Sunlight cannot reach far below the surface. Beyond roughly 300 meters, darkness dominates, and temperatures approach freezing. And yet, life finds a foothold along the seafloor. Hydrothermal vents release superheated, mineral-rich water into the cold ocean. These vents create steep chemical gradients, differences in temperature and composition that provide energy. Here, simple molecules assemble into more complex structures. Microscopic organisms appear, feeding on chemical reactions rather than sunlight. These single-celled bacteria represent the earliest known life on Earth. For hundreds of millions of years, life remained simple. No eyes, no limbs, no voices, just cells dividing, surviving, adapting. Progress is slow, almost invisible. Then, around 3.5 billion years ago, something remarkable happens in shallow seas. Colonies of bacteria begin using sunlight as an energy source. These organisms, called stromatolites, build layered structures that rise from the seabed. Through photosynthesis, they transform carbon dioxide and water into glucose, a simple sugar. This reaction releases oxygen as a byproduct. At first, oxygen reacts with iron dissolved in the oceans, forming rust that settles onto the seafloor. Over time, these deposits become iron-rich rock layers that future civilizations will mine. As the oceans saturate, oxygen begins to accumulate in the atmosphere. The air itself changes, slowly, almost without notice. The oxygen released by these living structures begins to change everything. In the oceans, it binds with dissolved iron, turning it into rust that drifts downward, settling into thick layers of iron-rich rock. One day, far in the future, these layers will be lifted and shaped into bridges, ships, and cities. But for now, the greater transformation is happening above the waves. Oxygen seeps into the atmosphere, reshaping the very air that surrounds the planet. It becomes the single most important ingredient for complex life to exist. Without these ancient bacterial colonies, nearly every living thing we know would be impossible. And every time we take a breath, every quiet inhale, every gentle exhale, we are doing so because of their silent work. Begun billions of years ago beneath an ancient sun, that quiet transformation does not end there. Over the next 2 billion years, oxygen continues its slow, patient rise. It does not arrive in a rush or announce itself with drama. It seeps, molecule by molecule, into the oceans and the air, steadily widening the range of what life can become. As this invisible change unfolds, The rhythm of the planet itself begins to soften. Earth's spin, once frantic and fast, gradually eases as the moon drifts farther away. Days lengthen. Sunlight lingers where daylight once vanished almost as soon as it arrived. It now remains, warming the surface for longer stretches of time. Eventually, a single day lasts at least 16 hours. It is becoming clear that a planet is not built quickly. It is shaped through patience, repetition, and balance. 1.5 billion years ago, 3 billion years after Earth first formed, the surface still feels strangely quiet. There are no trees breaking the horizon, no animals moving across the land, no dinosaurs, no humans. Life exists, but it is subtle and hidden, confined to water, to microbial worlds too small to notice from afar. And yet, Earth now possesses something rare, something powerful enough to transform everything that rests upon it. Seen from space, the planet appears as a blue sphere, scattered with volcanic islands, wrapped in oceans, alive in a way no other known world is. Beneath that surface, calm. Deep forces are at work. Over millions of years, the islands begin to drift, not randomly, but carried by slow currents far below. The crust has fractured into vast plates, floating atop hotter, softer rock beneath. Deep in the planet's interior, the core remains unimaginably hot, hotter than the surface of the sun. This heat keeps the mantle in motion, and those slow movements push and pull the plates across the globe. When we allow time to accelerate, Earth seems restless, almost alive. Continents collide, fuse, stretch, and tear apart. Oceans open and close. Mountains rise and are worn away. Over more than 400 million years, this motion brings the land together into a single immense mass, a supercontinent, Rodinia. Along the shallow seas that fringe Rodinia, stromatolites continue their ancient work. For billions of years, these bacterial colonies have been quietly releasing oxygen into the world. Now the atmosphere is richer than ever before. The climate is warm and gentle. Surface temperatures hover around 30 degrees Celsius. Days stretch to about 18 hours long. In many ways, the planet seems ready. And yet, despite all this preparation, the surface still feels empty, more like a distant red planet than the living Earth we recognize. Then, without warning, the stillness breaks. Rodinia begins to tear itself apart. We move above what will one day become Washington State. Around 750 million years ago, deep within the planet, heat is rising. It stretches the crust, thinning it, weakening it, pulling it apart centimeter by centimeter. Year by year, there is only one force capable of ripping a continent in two, and it comes from the planet's own heart. As the crust splits, molten rock surges upward. Volcanoes erupt along the fractures. Vast and numerous, they pump enormous quantities of carbon dioxide into the atmosphere. The sky fills with gas and ash. Rain falls, but it is no longer gentle. Carbon dioxide dissolves into the rainwater, forming acid rain that washes across the freshly exposed rock. The rocks absorb the acid, and with it, the carbon dioxide. and there are many rocks exposed now, more than at any time before. As Rodinia breaks apart, immense surfaces of fresh stone are revealed. They act like a sponge, pulling carbon dioxide out of the atmosphere and locking it away inside the Earth itself. The balance shifts dangerously, with less carbon dioxide left in the air. There is nothing to trap the sun's warmth. Heat escapes back into space. The temperature drops rapidly. In just a few thousand years, Earth plunges into deep cold. Surface temperatures fall to around -50 degrees Celsius. Ice begins to spread. What was once ocean becomes frozen in what will one day be southern Australia. Towering walls of ice rise, thousands of meters high. The ice advances relentlessly, and as it grows, it reflects more sunlight away from the planet, accelerating the cooling. A second ice sheet spreads from the opposite hemisphere, slowly, steadily. The two advance toward the equator. Eventually, they meet. Ice up to 3 kilometers thick covers the planet. From pole to pole, Earth is locked inside a frozen shell. Nearly all sunlight is reflected back into space. The world becomes a vast snowball, drifting cold and silent through the dark. For 15 million years, the ice holds. It seems impossible that life could survive this. Not even the sun appears capable of rescuing the planet. But deep beneath the ice, the Earth does not stop. Volcanoes continue to erupt, forcing their way upward through cracks in the frozen surface. They release carbon dioxide, year after year, before the freeze. Rocks absorbed this gas. Now the rocks are buried beneath ice. There is nothing to capture it. The carbon dioxide accumulates in the atmosphere, forming a thick, invisible blanket. Slowly, the trapped heat begins to build. Temperatures rise. After 15 million years, the ice begins to weaken. Meltwater pools. The frozen shell fractures. As the weight of the ice lifts, the crust rebounds upward, cracking further and allowing even more volcanoes to erupt. Each eruption releases more carbon dioxide, accelerating the warming. During the long frozen age, another quiet transformation has been taking place. Ultraviolet light from the sun reacts with water molecules trapped in the ice, producing hydrogen peroxide, a chemical rich in oxygen. As the ice melts, this compound breaks apart, releasing large amounts of oxygen into the oceans and atmosphere. After millions of years of stillness, the planet awakens. Around 600 million years ago, Earth feels utterly changed. The air is warm again, like a long-awaited summer day. The oceans surge with meltwater. Days now last about 22 hours. The seas are rich with oxygen and nutrients. The conditions are perfect for life to experiment. Before the freeze, life had remained simple. Somehow, some organisms endured the cold, surviving in sheltered pockets beneath the ice. Now, in these oxygen-rich waters, they diversify with astonishing speed. By 540 million years ago, the oceans are no longer quiet. Plants spread across shallow seas. Armored creatures appear, protected by plates and spines. Wiwaxia crawls along the seafloor, its body shielded against predators. Oxygen allows bodies to grow larger, stronger. Skeletons form. Worms burrow. Sponges filter the water. Trilobites appear in vast numbers, their hard shells preserving their shapes in stone. They are distant relatives of insects and crustaceans, thriving in every corner of the ocean. Predators follow. Anomalocaris patrols the water, reaching lengths of about 60 centimeters. Its large eyes scan the darkness. Its grasping limbs and sharp mouthparts make it a formidable hunter. Amid this explosion of life, small creatures drift almost unnoticed. Pikaia, only a few centimeters long, carries a simple internal structure, a flexible rod running along its body. It is the earliest hint of a spine. Over immense spans of time, this simple feature will evolve into the backbone that allows bodies to rise, to walk, to stand upright. We entered the ocean expecting to find life broken by catastrophe. Instead, we have arrived in a world overflowing with movement. Trilobites scavenge across the seafloor. Predators prowl. Creatures are beginning to take on forms that feel strangely familiar. If the oceans are alive with such richness, then the land above cannot remain empty for long. Beyond the water's edge, unimaginable worlds are waiting, strange landscapes, unfamiliar creatures, and possibilities still hidden just beyond our sight. To find the moment when those possibilities begin to surface, we have to look far back to a quieter chapter in deep time. We are looking for life on land. 460 million years ago, once again, the slow and relentless movement of Earth's plates has reshaped the surface. Continents that were once scattered have drifted, collided, and separated, guided by forces operating far beneath the crust. Below us now lies a vast landmass known as Gondwana. Stretching across much of the southern hemisphere, the climate is warm, hovering around 30 degrees Celsius, and the air holds oxygen levels close to those we live with today. By every familiar measure, this world should feel alive. Forests should blanket the land, and creatures should crawl, fly, and roam across the surface. But the land is strangely quiet, almost empty. Only a few dark patches of algae cling to damp ground near the edges of water, while the rest of the surface feels bare and exposed. The reason for this absence is not hidden in the soil, but written in the sky above. The sun pours down radiation with nothing to stop it. In the oceans, water absorbs and scatters this energy, protecting delicate chemistry and fragile life. On land, there is no such shield. Complex life, no matter how successful it is in the sea, would be torn apart at the molecular level within moments. The surface, for now, remains an unforgiving place, yet high above, far beyond clouds and weather, something subtle is unfolding. Nearly 50 kilometers overhead, sunlight strikes oxygen molecules in the upper atmosphere. The energy splits them apart, and when they collide again, a new gas forms, ozone, molecule by molecule. An invisible layer begins to surround the planet. This ozone layer is thin and fragile, easily disrupted, yet its effect is profound. It absorbs the most dangerous wavelengths of the sun's radiation before they can reach the surface. Over the next 120 million years, this layer slowly thickens, not all at once, and not evenly, but steadily enough that the land below begins to change. Radiation weakens, and surfaces that were once lethal become merely harsh. then slowly tolerable. Without this ozone shield, life on land would never exist. With it, the planet opens a door that had been closed since its birth. Protected at last, life begins to experiment. Small plants appear, hugging the ground, low and resilient, resembling mosses pressed close to the surface. They draw moisture directly from the air and thin soil, spreading cautiously across the land. These plants carry out a familiar chemistry. Using sunlight, they make food, and in doing so, they release oxygen. As they spread, oxygen levels rise further, strengthening the ozone layer and reinforcing the safety of the land. A feedback loop emerges, one that quietly transforms the surface into a place where complex life can survive. The planet is changing itself from the inside out. 375 million years ago. Long after this transition begins, a creature leaves behind a record of that delicate moment between worlds. Its remains will one day be found in what will become a remote valley on Ellesmere Island in Canada. The creature is called Tiktaalik. At first glance, it looks like a fish, but closer inspection reveals something new. Tiktaalik has a flexible neck, allowing it to lift its head independently of its body. Its fins contain bones arranged like wrists and elbows, strong enough to support weight. It can push itself up, rest in shallow water, and even pull its body briefly onto land. It does not abandon the water completely, but lingers at the boundary, testing a world that is only just becoming survivable. Over the next 15 million years, creatures like Tiktaalik continue this experiment. Their fins strengthen, their bones thicken, and their lungs become more efficient. They spend longer stretches breathing air and less time submerged. Gradually, they become tetrapods, animals with 4 limbs capable of bearing weight on land. By 360 million years ago, these pioneers are no longer visitors. They live on land. From creatures like these will descend every 4-limbed vertebrate that follows dinosaurs, birds, mammals, and eventually humans. The step from water to land is complete, and the consequences will echo for hundreds of millions of years. As animals step onto land, plants are already transforming it. Mosses and ferns spread rapidly, some growing into towering forms more than 30 meters tall. Their roots stabilize the soil, their leaves slow erosion, and entire ecosystems take hold. The surface of the planet becomes structured, layered, and alive. Among these plants appears a quiet but revolutionary innovation: the seed. Until now, plants have relied on spores, tiny reproductive cells that require constant moisture to survive. Spores tie life to water and limit how far plants can spread. Seeds break that dependency. A seed contains stored food, water, and genetic instructions sealed within a protective coat. It can survive dryness, cold, and long stretches of time. This simple structure allows plants to move inland, far from rivers and coastlines. Forests spread across continents, replacing bare rock with vast green landscapes. These forests pump enormous quantities of oxygen into the atmosphere. The air grows thick with possibility, rich enough that we could stand here and breathe comfortably. Life has traveled an extraordinary distance, from a molten sphere of rock and dust to a world bursting with color and movement. Yet humans will not walk these forests for another 360 million years. Something passes overhead. A dragonfly glides through the air. But it is enormous, with wings spanning nearly as wide as an eagle's. This is Meganeura. Elevated oxygen levels allow its respiratory system to function efficiently even at such a large size. Below, the land crawls with life. Millipedes stretch nearly 2 meters long. Scorpions grow to the size of wolves. Cockroaches, spiders, and countless other arthropods roam the forest floor. These animals were among the earliest to colonize land, and they have been evolving for hundreds of millions of years already. They resemble modern insects, but they exist in a world governed by very different atmospheric rules. Among the undergrowth, a small lizard-like creature moves carefully. It is called Hylonomus, and it carries one of the most important evolutionary innovations of all. Earlier land animals still return to water to lay their eggs. Hylonomus does not. Its eggs contain everything the developing embryo needs: water, nutrients, and protection sealed inside a membrane. This is the amniotic egg. It allows animals to reproduce entirely on land, severing the last major tie to the sea. With this innovation, life truly conquers the continents. With abundant life comes abundant death. Dense forests shed leaves and trunks, and plant matter accumulates in thick, waterlogged layers over hundreds of millions of years. These layers are buried beneath sediment. Heat from the Earth's interior and pressure from above transform them into seams of coal. Every piece of coal burned in the future comes from plants that died roughly 300 million years ago. Hidden beneath decay, life continues to stir. Seeds germinate, forests return, and the land seems fully conquered. For a moment in deep time, it feels as though life has finally secured its place. 250 million years ago, herds of massive animals graze the plains of what will one day be Siberia. They are not dinosaurs, which will not appear for another 20 million years. These are Scutosaurus, large armored plant eaters, distant relatives of turtles. Evolution has pushed life to impressive extremes. Nearby, a Gorgonopsid waits. It is the most efficient land predator of its time. Equipped with long saber teeth, it watches its wounded prey weaken from blood loss. Then the ground beneath them begins to warm. This is not a single volcano. Deep beneath the crust, an enormous plume of hot mantle material is rising. It forces molten rock through vast fractures in the Earth's surface. Lava pours out continuously, spreading across an area that will eventually rival the size of the United States. The lush world begins to collapse on the far side of the continent. White material falls from the sky. It looks like snow, but the temperature is around 20 degrees Celsius. This is ash, carried more than 16,000 kilometers from the eruptions. It burns, suffocates, and poisons. Animals die where they stand. 250 million years ago, the greatest mass extinction in Earth's history is underway. Volcanoes release enormous quantities of sulfur dioxide. Rain turns the gas into sulfuric acid, burning everything it touches. What begins as a regional disaster becomes global. Carbon dioxide floods the atmosphere. Temperatures rise. Water evaporates. Vegetation dies. The oceans warm and lose oxygen. and entire ecosystems suffocate. The seas turn pink as algae dominate waters where nothing else can survive. Methane trapped beneath the seabed is released as temperatures rise. This powerful greenhouse gas drives temperatures even higher, pushing the planet beyond recovery. The eruptions continue for 500,000 years, and lava blankets the land in layers nearly 6 kilometers thick. 95% of all life is wiped out. Only a handful of creatures survive, burrowing underground and feeding on anything they can find. The mass extinction resets the evolutionary clock 250 million years ago. We are almost back where we began, on a planet that is nearly lifeless once again. But even in that silence, time does not stop. The planet continues to turn. Oceans continue to circulate, and chemical cycles slowly begin to settle into new balances. Over tens of millions of years, the violence fades, the extremes soften, and life, fragile and tentative, finds room to return. It has been 50 million years since nearly all life on Earth was erased, and the planet is almost unrecognizable compared to that moment of devastation. We are now 200 million years in the past. The scars of catastrophe have not vanished, but they have softened. The world is quieter, steadier, as though it is slowly learning how to breathe again. There is only one vast supercontinent now, stretching from pole to pole. It is called Pangaea, after the trauma of mass extinction. The planet has entered a long process of recovery. Temperatures are stabilizing after extreme swings. Ice rain, once relentless, is gradually neutralized as chemical cycles regain balance. Vegetation returns in patches, then spreads, binding soil and calming erosion. With 95% of all life wiped out, competition is minimal. The planet is open, almost empty, waiting. In that emptiness, opportunity takes root. From the small number of reptiles that survived the extinction, a new group begins to diversify. They are dinosaurs. At first, they are not giants. One of them, Amargasaurus, stands around 4.5 meters tall. Its size makes it powerful, but also slow and exposed in a world still learning how to stabilize. Size is not always an advantage. Nearby, two smaller predators move with speed and precision. Dilophosaurus, alone. One of them would not dare attack such a large animal. Together, they coordinate. Agility and cooperation allow them to overcome strength. This is how the new ecosystems work: trial and error. Balance, rebuilt through countless encounters. Dinosaurs spread across the land, filling niches left empty for millions of years. Yet even as they rise, the planet itself refuses to be tamed. Earth remains restless and volatile. In places, the crust is thinning. Stretched by forces deep below, lava breaks through the surface. Earthquakes ripple through the ground, along what will one day be the eastern edge of North America. The same tension builds. The plates are moving again. 190 million years ago, Pangaea begins to break apart. A vast rift opens, and a chunk of land pulls away, forming a new ocean basin known as the Tethys, over what will one day become the Middle East. Warm waters spread. Ocean currents push nutrients upward from the depths into coastal zones, where nutrients rise. Life follows. Fish gather in immense numbers. Plankton blooms fill the water. And where there is life, there is death. Dead fish and microscopic organisms drift downward, carpeting the seafloor. Over the next 10 million years, layers of sediment bury this organic matter. Heat from below and pressure from above slowly transform it. Ancient fish and plankton become oil, every drop of fuel that will one day power vehicles. Every piece of plastic, the paint on walls, the fibers in carpets, even the soap used to wash hands, all trace their origins back to this quiet burial beneath ancient seas. Farther west, the North American plate continues to move away from the European and Asian plates. The motion is slow, about 2.5 centimeters each year, roughly the same rate at which fingernails grow. It feels insignificant in the moment, but when time accelerates, the change becomes dramatic. A new ocean opens beneath us. Cities that do not yet exist drift apart. Montreal moves away from Marrakesh. New York separates from West Africa. The world we recognize begins to take shape. The widening gap fills with seawater, forming the Atlantic Ocean. At its center, something extraordinary is happening. The seafloor is tearing open, pushed upward by molten rock from deep within the earth. A vast ridge of volcanoes rises, longer than the Rocky Mountains and taller than the Himalayas. Lava pours out, cools, and hardens, creating new ocean floor. This process continues for millions of years, pushing continents apart and reshaping the planet. This constant geological activity is what makes Earth restless, creative, and unique. And each time, the planet reinvents itself. The life upon it must adapt. Some creatures respond by returning to the sea. Reptiles whose ancestors lived on land evolve fins and streamlined bodies. Ichthyosaurs emerge, moving through the newly formed Atlantic. One of them reaches 6 meters in length and can travel at speeds of around 40 kilometers per hour. It becomes one of the fastest, most efficient predators the oceans have ever known. For 50 million years, it rules the seas. Then a challenger appears. Plesiosaurs. Some grow longer than a bus, with bodies as heavy as trucks. Their jaws are immense, delivering bites far more powerful than those of modern great white sharks. Teeth longer than 30 centimeters line their mouths. The oceans become arenas of colossal hunters. Meanwhile, above the waves, the land continues to change. What was once solid ground beneath our feet is now deep ocean. The place where we once watched herbivores graze and predators stalk is gone. Swallowed by the Atlantic, the dinosaurs adapt. Their world is different, but they remain dominant. For 165 million years, dinosaurs thrive. They survive volcanic eruptions, earthquakes, and the slow tearing apart of continents. They appear unstoppable. They are among the most successful groups of animals the planet has ever produced. Yet nothing on Earth is invincible. In the shadows, another group persists. Mammals. They evolved from the few small creatures that survived the mass extinction 185 million years ago. Compared to dinosaurs, they are insignificant. They are hunted. They hide. Most live in trees or underground. Many are active only at night. Mammals pose no threat to dinosaurs. Nothing does. Nothing on Earth. But the danger is not coming from Earth. Far out in space, a massive object is on a collision course with the planet. A fragment of ancient rock, left over from the formation of the solar system. This asteroid measures about 10 kilometers across. Larger than Mount Everest, it is traveling toward what will one day be the Gulf of Mexico. Near the Yucatan Peninsula, everything happens too quickly to comprehend unless time slows. In the final moment before impact, the asteroid's trailing edge is still nearly 11,000 meters above the surface, the height at which modern commercial aircraft fly. Then it strikes. The force of the impact is beyond anything the planet has experienced since its formation. The asteroid and the rock beneath it vaporize instantly. Energy equivalent to millions of nuclear weapons is released in a fraction of a second. A shockwave races outward faster than sound, flattening everything in its path. Within minutes, thousands of kilometers away, Earth is under attack from every direction. Boulders the size of city blocks rain down. Earthquakes shake the ground. Tsunamis surge across coastlines. But this is only the beginning. A towering plume of molten rock and dust erupts into the sky and spreads across the globe. The atmosphere itself begins to glow. The entire sky acts like a furnace. Surface temperatures climb to around 275 degrees Celsius. Vegetation ignites spontaneously. Fires rage across continents. Even months later, smoke and ash continue to block out the sun. With no sunlight, plants die. Without plants, animals starve. Food chains collapse. Against such an onslaught, survival seems impossible. 65 million years ago, the dinosaurs are finished, blasted, burned, and starved. Their 165 million year reign comes to an end. But extinction creates space. While dinosaurs perish, mammals endure by living underground. They avoid the worst of the heat and fires by eating almost anything. They survive when specialized feeders cannot. In the darkness, in the long aftermath, they persist. These small, overlooked creatures become the unlikely inheritors of a world once ruled by giants. As one story ends, another quietly begins. And in that fragile beginning, a question hangs in the silence of deep time. Could this be our chance? Time offers its answer slowly. The dinosaurs are long dead now, and their absence has changed the planet's mood in a way that is hard to describe until you stand inside it. The ground is no longer trembling under the weight of giants, and the forests are not held in a constant state of alarm. The world feels quieter, as though it has set down something heavy and is finally letting its shoulders drop. In that quiet, our mammal ancestors begin to unfold into forms that would have been impossible in the old age of thunder and teeth. We come to a lake 47 million years ago, in a place that will one day be Germany. And the scene feels almost gentle. The air is warm and soft, and the water lies still, like a sheet of dark glass. The shore is alive with plants, and insects stitch invisible paths through the green. It seems like the perfect place to spot the small, quick mammals that have been testing the edges of this new world. What we find is not a rodent darting into cover, but something that carries a different kind of attention in its face. She has larger eyes and a brain shaped for a more complicated way of moving through life. Her name, in our own time, will be Darwinius Masilai. and many will simply call her Ida. She looks nothing like a human, and yet she is not as far away as she seems. Fossil evidence from our time suggests that creatures with bodies like hers sit close to the early branching paths that can lead toward monkeys and apes. And eventually to us. She is not a promise carved in stone, and not a guaranteed direct ancestor. But she is a window into an early primate world, where the basics of our story are beginning to appear. Look closely at what her body is built to do, and you can feel how the planet is shaping minds as much as muscles. Life in trees demands precision. Branches are honest in a brutal way misjudge a distance, and you fall, so larger. Forward-facing eyes matter because they help a brain measure depth. Hands that can grasp matter because leaves and bark do not offer the same stable footholds as ground. A nervous system that can coordinate movement matters because survival depends on timing and balance. In a quiet way, these forests are asking for better vision, steadier hands, and a brain that can hold a map of the world inside it. The lake itself carries a darker secret. It sits in a volcanic crater, and the ground beneath it still exhales gases from deep within the earth. At times, the lake releases noxious clouds, heavy and low, slipping across the surface like an invisible tide. One day, that breath from below is enough to overwhelm Ida. The water that takes her life also becomes her guardian. Down in the depths, oxygen is scarce, and without oxygen, decay slows, scavengers do not thrive, and bacteria cannot work their usual fast unraveling. Sediment settles gently over her body, sealing it away from time's rough hands. Much later, when the lake is gone and the sediments have become stone, her descendants will find her. People will lift rock from rock and discover a small primate preserved with astonishing detail. And something in that delicate shape will feel familiar. Not familiar like a mirror, but like an old family resemblance you cannot quite name. In that ancient body, we begin to sense the earliest outlines of a story that will one day call itself human. It is a quiet kind of recognition, the kind that does not shout, but settles in slowly, like dawn. Around this time, the Earth itself feels almost like the planet we know. 47 million years ago, the atmosphere is much like our own. The average temperature is around 24 degrees Celsius, and a day lasts just under 24 hours. Close enough to feel natural in the bones. The air is breathable. The seasons have a rhythm, and the oceans sit where oceans belong. If you could stand here without the knowledge of time, you might believe you had simply wandered into a warmer version of home. But almost is a word the earth loves. Beneath the surface, the plates are still moving, and they never truly rest. Continents ride on the backs of these massive slabs of crust, carried by slow currents in the mantle below. The motion is so gradual it feels like stillness until you remember what millions of years can do. The planet's calm face is held up by deep, ongoing work. And sometimes that work becomes visible in a sudden, astonishing way. One of the most dramatic examples is happening as India drifts north. The Indian plate moves toward Asia like a patient, unstoppable traveler. And when it arrives, there is no gentle merging. The Indian and Asian plates lock together in a struggle that neither can win. Ocean crust that once lay between them is squeezed, folded, and destroyed. and the edges of the continents begin to buckle. Rock crumples the way fabric does when pushed from both sides. The Earth does not split here, it thickens. Along a crumple zone, stretching roughly 2,400 kilometers, the ground rises. At first, the new mountains reach around 1,500 meters. Later, they rise to around 4,500 meters. And still, they keep climbing. In time, peaks push past 8,000 meters, lifting into thin air and high winds. This is the birth of the Himalayas, a mountain range formed not by eruption, but by collision and compression. A slow bruise turned into stone. And there, at the highest point, stands Mount Everest. Its summit reaches into the jet stream, near the same altitude where commercial aircraft fly. The air up there is thin and sharp, and the cold is relentless. Snow gathers, ice thickens, and what falls from the sky stays for long stretches of time, held in place by altitude and shadow. When that snow melts, it does not simply disappear. It becomes water with a destination. It pours downward into great rivers that will one day shape entire civilizations. The Ganges, the Indus, the Yangtze, and the Yellow River are fed by this enormous high-altitude reservoir. The Himalayas behave like a vast water tower, storing winter in frozen form and releasing it into warmer months. Year after year, one day, the rivers born here will supply water for almost half the world's human population. Even before people arrive, the mountains steer winds and rainfall, shaping monsoons and shifting climates across Asia and beyond. The mountains also do something quieter, something that takes longer to notice. As they rise, they are worn down by rain, ice, and time. Erosion breaks rock into smaller pieces. Those pieces travel in rivers. And in that journey, chemical reactions can pull carbon dioxide from the air and lock it into minerals. The world's great mountain building events can, over long spans, influence how warm the planet becomes. It is another reminder that Earth is not just a stage for life, it is an active participant, constantly rearranging the conditions under which life must survive. Time moves forward, and by 20 million years ago, the planet looks almost complete in a way that feels uncanny. The continents and oceans sit in the patterns we recognize. The Atlantic is open. The Pacific holds its vast blue weight. The poles have their cold authority. If you traced coastlines on a map, you would be drawing something close to the modern world. There is just one obvious absence, one silence where a familiar voice has not yet arrived. There are no humans. For humans to evolve, something must shift in the tapestry of climate and landscape. Along Africa's east, the crust begins to stretch. The plates that make up the Earth's surface pull in different directions, and a great rift starts to open like a seam slowly unzipping. 4 million years ago, this rift extends for nearly 6,000 kilometers. Along its edges, mountains rise, valleys sink, lakes form in elongated basins. The land becomes a landscape of cliffs and high ground, as though the continent is being gently torn and reshaped at the same time. In the trees, apes live as they have for ages, moving through branches with confidence. It would be easy to imagine they could remain in those trees forever, but the world below them is changing its mind. The growing mountains act like a wall, interfering with the movement of moist air from the Indian Ocean. Moisture that once traveled inland now drops its rain on the ocean-facing side, leaving the interior drier. A rain shadow forms. Seasons shift. The region becomes hotter and less forgiving. The lush rainforest begins to retreat, and open savanna spreads in its place. This is not a sudden switch, but a slow transformation, one that happens in fits and starts across generations. Trees thin out, grasses expand, food becomes more scattered. In a forest, you can travel from meal to meal by moving through continuous canopy. On a savanna, you must cross open ground. You must walk farther. You must see farther. The new environment presses on bodies in subtle ways. Knuckle walking across long distances costs energy, and it keeps the face pointed down, limiting what can be seen. Standing upright changes that. It raises the eyes, letting an animal scan the horizon. It reduces the amount of direct sunlight hitting the body's broad surface, and it lifts more of the body into cooler air. It frees the hands to carry food, to carry tools, to carry infants. It turns the body into a traveler, not just a climber. The shift to walking on 2 feet is not a grand plan or a heroic step toward destiny. It is an answer to a problem. It is a practical response to a world that has become more open and more demanding. Over time, anatomy follows behavior. The pelvis reshapes. The spine develops curves that balance an upright stance. The foot becomes a platform designed for long-distance walking. The skull begins to sit differently on the spine, favoring a posture that looks forward rather than down. It is the most important step in the human story, and it begins not with an ambition, but with a need. It feels almost unbelievable that the random movement of tectonic plates could begin a chain reaction that eventually leads to humans. Yet Earth does this repeatedly. It shifts a coastline, and life must adapt. It raises mountains, and rainfall changes. It opens an ocean passage, and climates reorganize. In Africa, the opening of a rift and the rise of mountains may have nudged our ancestors out of trees and onto the ground, into a life that required walking upright. Time moves forward again, and the world feels closer. 1.5 million years ago, a scene appears that could almost belong to the present. A man and a child walk across open land together. They are not modern humans, but they are unmistakably human-like in posture and movement. They belong to Homo erectus. Their bodies are built for distance. Their legs are long. Their gait is efficient. They can travel across landscapes that would have exhausted earlier hominins. In their wake, footprints press into soft ground. These are the first footprints like our own. The same pattern of heel-to-toe movement. The same weight shifting forward. It is a quiet kind of evidence, as tender as it is powerful, because it captures motion rather than bone. Homo erectus carries more than a body shaped for walking. This lineage is often associated with a more complex way of living, sharing food, traveling in groups, adapting to changing environments over long spans. The use of fire becomes a turning point for human ancestors. Fire offers warmth in colder nights, and it offers protection. It also changes food. Cooking breaks down tough plant fibers and softens meat, making calories easier to access. Over many generations, a risher, More reliable energy supply supports a brain that is expensive to run. The body and the mind begin to bargain with each other, trading one kind of investment for another. Our ancestors still have their own migration ahead. The journey out of Africa is not a single march, but a series of movements. A pause, losses, and new starts. Climate shifts open corridors and close them again. Rivers change course. Deserts expand and contract. Some groups vanish without leaving a trace. Others persist. And in persisting, they slowly redraw the map of human possibility. Then, 70,000 years ago, the planet changes its posture again. Sea levels begin to fall. Water becomes locked in ice elsewhere on the planet, and coastlines shift outward. The gap between Africa and Arabia shrinks, narrowing to around 13 kilometers. The Red Sea becomes shallow enough and narrow enough for a small group to cross. This crossing is not a grand armada. It is fragile people with limited supplies and enormous uncertainty, stepping into a world they do not yet know. These travelers are Homo sapiens. Scientists believe that every man, woman, and child living outside Africa today descends from perhaps 200 individuals in such early groups. The number is sobering, not because it feels dramatic, but because it reveals how close our story came to ending before it truly began. A disease, a storm, a failed season. Small misfortunes could have erased that line entirely. Survival is often less about strength than about being lucky enough, flexible enough, and connected enough to endure. Over time, these humans multiply and spread. They move into India, across Asia, into Europe. They adapt to new foods and new climates. They learn the rhythms of unfamiliar animals. They craft tools believed to fit specific tasks. And they build social bonds that let them share knowledge across generations. In a world that changes, memory becomes as valuable as muscle. While humans head north, the planet prepares another challenge. A giant wall of ice begins to spread south once more, as if the Earth and its inhabitants are about to meet head to head. Europe, 40,000 years ago, is changing quickly. It should be the height of summer, yet plants are frostbitten. Rivers are frozen. The air holds a sharpness that suggests winter has stopped obeying its usual boundaries. Natural changes in Earth's orbit, shifts in carbon dioxide levels, and the flow of warm ocean water around the planet begin to conspire toward cooling. The tilt of Earth's axis, the shape of its orbit, and the timing of seasons can change how sunlight is distributed. These are slow celestial adjustments, gentle in mechanism, but enormous in consequence. When less summer warmth reaches high latitudes, winter snow does not fully melt. It accumulates, year after year. Compressing into ice, the planet enters an ice age. Glaciers advance like silent animals, slow and powerful. Some move at around 30 centimeters a day, creeping forward with a patience that feels almost intentional. They are as high as skyscrapers in places, and they reshape everything beneath them. They grind mountains down. They gouge out basins. They carve valleys. They leave behind ridges of rubble, pushed and piled by their weight. The landscape is sculpted not in moments, but in long, steady pressure. Around 20,000 years ago, the ice reaches a peak. Much of the northern hemisphere lies under ice sheets, up to 2.5 kilometers thick. Trillions of liters of water are locked away as ice. Sea levels fall. Shorelines stretch outward. Land bridges appear where seas once flowed, between Siberia and Alaska. A strip of land rises from the ocean. It becomes a bridge between two vast continents, a gateway for humans moving from Asia into a new world. America becomes the last great continent to be colonized. The final major human migration of its kind, somewhere on that wide, cold corridor. The first Americans begin their long settling into landscapes shaped by ice and time. Then, 14,000 years ago, the forces that push the planet into deep cold begin to relax. The cycles that favored ice accumulation shift. The planet warms. Ice starts to retreat. The meltwater is immense, and it rushes into the scars left behind by glaciers. Great depressions carved by ancient ice fill with water, becoming the Great Lakes of North America. Rivers find new paths across newly exposed ground. Forests begin to return, slowly reclaiming regions that had been locked beneath ice for thousands of years. 6,000 years ago, the ice withdraws farther toward the poles. The world becomes more stable again. Coastlines settle into shapes we recognize. Seasons soften into familiar rhythms. After a 4.5 billion year journey, we have arrived back in the present. Back to our world, our time. For the first time, we can gather the fragments of this immense history and see them as one continuous story. We can understand how everything we have seen, ocean bacteria, walking fish, forest seeds, underground mammals, and migrating humans belongs to the same thread. We can see how the skies above us, the water we drink, and the ground beneath our feet are not separate miracles, but linked outcomes of a long chain of events. Water, the essential ingredient for life, arrived through ancient deliveries and was held here through balance and luck. Land rose and shifted through relentless tectonic motion. Oxygen accumulated through the quiet labor of microbes and plants. Each triumph and each disaster became a step along a trail that leads to here, to each of us, alive right now. And yet the story does not stop with us, or with this moment. The Earth will live for at least another 4.2 billion years. Everything we have witnessed across deep time is only part of what this restless, creative planet can become. The continents will continue to move. Oceans will open and close. Mountains will rise and be worn down again. Life will keep adapting, keep experimenting. And sometimes it will suffer losses that reshape the future in ways no one could predict. If you let your thoughts rest on that, there is a strange comfort in it. The planet has never been finished, and it is not finished now. Somewhere ahead lie wonders and terrors, strange creatures and unfamiliar landscapes, born from the same forces that shaped everything we have ever known. The continuation of Earth's story is still unwritten, waiting in time, as patiently as stone.